So it's it's a true pleasure to receive everybody that is joining and interested in the IronTract challenge, in the launch, let's call it the live launch of the second round. I assume that everybody's rather familiar with what's the IronTract challenge, what was the scope of round one, right? All about accuracy, big topics, accuracy and reproducibility in diffusion MRI, in tractography. So now the round one was already concluded, but there are some outcomes from that, some winners, some great algorithms, some pre and post processing algorithms. And now round two, it's all about the reproducibility upstream. So like to the tractography, to the orientation, reconstruction, and tractography. And yeah, so today is all about round two, and I'm very honored, very happy to have in this event the masterminds behind this challenge. So we will have today. Let me switch. Okay, so we'll start with Anastasia. All right, so from Martino Center, from Harvard, and she'll be telling us all about the challenge. Remind us why it is important, why everybody's contributing to this great cause. Then Chiara will give us some results, or will show the results from the first round, and as well, or more importantly, how can you also participate now in second round? So like a kind of a demo, like what are the steps, and also very happy to have here Gabriel. Is like one of the proud winners of the first round from EPFL. And it was very kind to volunteer to show us actually like a tutorial on how to use, how to port, how to share your codes in QMENTA platform. So like that's one of the new additions to the challenge, is like to add also the concept that algorithms and research are one step, but then what? How do you distribute, and how do you standardize in a way the distribution or deployment of these algorithms? So that's a twist that we're adding to the second round. So we will show us how we ported the pipeline to using the SDK, and want to make it a bit more challenging, more fun, more wanted to spice it up, the competition. So we'll have also three awards, three financial prizes that we'll be talking about them more in the end. So I'll give the floor to the important people here. Just wanted some technicalities, like, well, everybody's in the chat, so if in the meantime anybody has questions, just write in the chat, and we'll try to coordinate and interrupt as appropriate, and pass on the questions. Yeah. So again, welcome everybody, and I'll pass the stage to Anastasia, the virtual stage.
Thank you, Paulo, and thanks everyone for joining us. I'm going to try to share my screen, and yeah, try to dig through my 40 open terminals to find my slides. Okay. Can everyone see that? Okay. I like to say that this challenge was socially distanced before it was cool, because even back in October of last year, everybody participated remotely. We've never actually been in a room all together, for better or worse. It does make some things easier, but it will be nice to have an in-person reunion at some point. So anyway, so this is business as usual for us. So from me, just a few quick words of hashtag Friday motivation for why efforts like the IronTract challenge are important. So our goal is to come up with objective assessments of tractography methods in realistic data that reflect the ultimate use cases, and people will be using it in the brain. So it's important to have data for this objective assessment that are as close to the human brain as possible, while at the same time giving us getting us as close as we can to the ground truth. And at the end of the day, with tractography, we're not really quite sure yet what the failure modes are, we have some assumptions on what they are, but until we figure out what the failure modes actually are in the brain, it will be hard to simulate them realistically as well. So why it's important to have this kind of objective assessment from the point of view of the users of the methods who simply want to produce results for their studies, it's important to be able to take the guesswork out of choosing among all the different methods out there. And from the point of view of the developers of the method, it's important to accelerate and democratize the adoption of new methods, because as we know, people tend to just use whatever they've always used. You know, I use VI since 1995, and it'll be my text editor until the day I die. So I can't cast any stones in that regard. People just tend to go with whatever has worked either for them or for other people, whatever has gotten papers published. And so if you're a developer and you come up with a new method, it's hard to get over that barrier to get people to try your method out. And so for that, it's important to have an objective way to show that your method works. And more than accelerating the adoption, it's also about democratizing it. So if you come out of absolute nowhere and you have a great idea and you can get it to work, it shouldn't matter, you know, how loud you are or who your friends are or, you know, how many followers you have on Twitter. You should be able to get get users to adopt your method. And for that, you need some numbers, some concrete way to show that it works well, and a platform to get that message out to the community. So that's what we're trying to lay the groundwork for here. And so before we begin with the details of what and how, I would like to acknowledge the people who got the challenge off the ground. So on our end at the Martino Center, Chiara, whom you'll hear from in just a little bit, as well as Robert, who helped a lot with the initial frantic testing when we were setting this up. On the anatomy side, of course, from the University of Rochester, Suzanne Haber and Julia Lehman. And none of this would have been possible if Suzanne hadn't walked into my office a few years back, wanting to do diffusion imaging on some of the brains that she was doing tracer injections in. And so they are the ones who provide all the anatomical expertise, and, you know, they ground truth our ground truth. And of course, on the informatics side, the QMENTA team. So very quickly after I approached Vesna about running the challenge through the QMENTA platform, the team had set it up within a couple of months. Everything was running, and they donated their time very generously, both to set it up as well as to support the platform for all the participants throughout the challenge. And so for us, this has been a lifesaver. So it takes the bookkeeping for all of this out of our hands, and that's all done by the platform, and we can focus on the science. And of course, I would be remiss not to acknowledge the heroes of the first round of IronTract. So of all the different teams that signed up, these are the leaders that persevered and made it all the way to the finish line. And for that, we salute you. So if you want to add your face to this pantheon, now's the time to participate, and you'll hear how in just a couple of minutes. And I should say that I threatened that I would use deepfakes for anyone who wouldn't send me their photo on time, but there are no deepfakes here. These are all the actual humans. Last but not least, there is more to come. There's more IronTract to come, hopefully. So a bit of good news, which is always nice to get these days, not very common. So we do have new funding that is pending from the National Institutes of Health. A new project that's called Bridging Diffusion MRI and Chemical Tracing for Validation and Inference of Fiber Architectures. And at this point, I can say it without really jinxing it. It's far along, you know, barring, of course, a catastrophic event like, I don't know, the US federal government collapsing between now and December 1st when this grant is supposed to start, but that wouldn't happen, right? There's no reason for that to happen. So among all the different things that this project is supposed to support is to automate the analysis of the tracing data. And that's a big bottleneck here. So the reason that we only have a couple of injections is that it can take months for somebody to label just a single injection manually. And you'll see from the results of the first round that Chiara is going to summarize why it's important to have multiple cases. So the goal here is to automate it, do high throughput analysis of the tracing and histology data, get us more ground truth and more IronTract. And if you want to contribute to that effort, join our team as a postdoctoral fellow at the Martino Center to work on this and other projects. And you can email me if you're interested. Okay, so with that, please grab your time zone appropriate beverage. This may or may not be Irish coffee. And I'll give it over to Chiara. Thank you.
All right. Okay. Hi, everyone. Can you see my screen? Okay, great. Okay, yeah, so as Anastasia just said, I'm gonna now present results from round one. Before getting into the results, though, I just want to spend a couple of minutes highlighting what are the unique characteristics of the IronTract challenge. So we all know the gap in spatial resolution and the indirect nature of the measured signal make diffusion MRI tractography prone to reconstruction errors. And previous validation challenges have addressed the accuracy of tractography techniques and shown its limitation in correctly reconstructing white matter structures. However, these prior challenges use diffusion data that had been either sensitized or acquired with single low B value, limiting the number of methods and acquisition schemes to be assessed. In particular, it is not clear for this reason whether we can draw any conclusions from these challenges and know whether these are applicable to widely available acquisition schemes like the Human Connectome project. Also, these challenges often compare ground truth and diffusion MRI data in different brains. So what we want to tackle with the IronTract challenge was try to address this gap by investigating which methods and processing strategies lead to optimal tractography accuracy for the two-shell HCP scheme, but also investigate whether those methods could achieve even higher accuracy with a different acquisition scheme. So for this reason, this challenge, as I said, has some unique characteristics compared to the previous ones. So it has data both from a training and a validation case, which allows us to evaluate how two different anatomical profiles can affect the accuracy of tractography and assess consistency of methods across different anatomical scenarios. We made available data with different diffusion schemes, which allows to evaluate a wider range of methods, compare differences across sampling schemes, and evaluate optimal methods for specific acquisition schemes, like, for example, the Human Connectome project. We asked participants to upload tractography results obtained at multiple thresholds, so that for each tractography volume, true and false positive rates were compared by voxel-wise comparison to the tracer data. And this allows to better investigate the sensitivity specificity trade-off and compare the different methods at the same false positive rate threshold. All right, so more in detail, we have, for this challenge, we have data from 2 monkey brains that serve as training validation case. And for both of these, we have in vivo tracing data from 2 different injection sites in the anterior frontal cortex and ventrolateral prefrontal cortex, respectively. And we also have diffusion MRI that we distributed both in the acquired DSI version and in the resample HCP. So for round one, data were shared through the QMENTA platform at 2 different time points. We first shared the training data set that participants could use to test and optimize their methods on the basis of the score. They could visualize the QMENTA platform, and then only in a second moment, we released the validation data, and this time participants were blind to their score. We then evaluated all final submissions and ranked them differently on the base of the scheme used. In terms of number for round one, we had 30 teams registering to the challenge with a total number of 226 submissions, of which 187 training and 39 validation. However, we then had a final number of 17 submissions for the validation data from 12 different teams. Participants used both common off-the-shelf algorithms and also more in-house developed algorithms that included reconstruction methods like spherical deconvolution, GQI, or compartment models. We have roughly an equal number of probabilistic and deterministic tractography algorithms. All right, so in terms of results, I'm showing here the ROC curves for all the submissions for the HCP acquisition scheme for the training case. And this are the overlaid ROC curves for the DSI data. Although there obviously is a trade-off between true and false positive reconstructions, most submissions achieved 80% sensitivity within 30% false positive rate. Now, these are the results for the validation case for the HCP data again, and for the DSI acquisition schemes. In the validation case, many submissions remain below the 80% sensitivity cap. So for both training and validation case, we then looked at the accuracy measured as the area under the curve for different settings across submissions. Overall accuracy is higher for the DSI scheme. Interestingly, while both probabilistic and deterministic tractography and most methods seem to perform fairly similar for training data, probabilistic tractography and spherical deconvolution showed much higher accuracy in the validation case. And the same is true for the use of additional mask to constrain tractography. Then having tractography results at different thresholds allowed us to compare methods at the same false positive rate. So for the same FPR, we look at the sensitivity in more detail for the validation case. And we want to try to understand where true positive and false negative tractography reconstructions were located. So we labeled the main bundles the tracing was projecting to, and then we computed the ratio of true positive voxel for each bundle for each submission. So here the different colors represent the different bundles. On a positive note, you can see most submissions correctly reconstructed bundles close to the injection point, while most of them failed to correctly recover bundles far from the injection point and located as splitting regions. So what can we conclude from this first round? So tuning the tractography analysis improves sensitivity. However, optimizing data analysis with respect to one injection site does not really guarantee optimality for another. Some methods do seem to be more robust than others, as they could achieve consistently high performance in both datasets. The DSI acquisition scheme led to higher accuracy overall. However, when the analysis methods were optimized, the HCP scheme may achieve similar accuracy as a more demanding acquisition scheme. Then a combination of probabilistic spherical deconvolution, use of additional mass to constrain tractography provide the highest sensitivity values and also resulted the best method for the HCP acquisition scheme among the ones submitted. Then finally, when looking at submissions at the same FPR, we can see false negative across all submissions, but mostly located at splitting regions. Most importantly, across all submissions, two strategies seem to significantly improve results accuracy, and those were use of additional post-processing filtering and the use of additional masks based on anatomical knowledge to constrain tractography. So we asked ourselves what would happen if all participants applied these steps, and this is what motivates round 2. Where we are asking participants to run their tractography method on harmonized pre-processed data and to post-process their data using the two winning post-processing strategies. Round 2 will be kindly hosted again by QMENTA, and this time we will also feature monetary prizes for the winners. The new deadline is November 8th, and I would go on and tell you everything about it now, unless I guess there's some question now. All right, we don't want to take any question.
And nobody asked while there's a question, but like for later about publications.
Okay, so I'll go on and talk about how to participate in round 2. I'll show you all the steps you need to take from the registration to the final submission. So the very first step is to register to the challenge. This is only true for new teams that haven't registered yet. Registration form can be found on the IronTract website, and it is required in order to receive a single use access codes that will be sent to the contact person of your team. The team name will be public, so we ask you to please not include any words that can identify your institution, lab, or individual members of the team. All the other fields that you enter below will be known only by the challenge organizer. So once you do this, you can go to the QMENTA website, and the first time here, you need to hit register. And here you put your name and email, and the most important thing, you need to insert here the activation code that you received after registering. Each member of your team can then create an individual account on the QMENTA platform using their own email address in one of these access codes. Accounts created with your team's access codes have access to each other's data on the platform. Right. Once you have done that, you can log in into the QMENTA website, and this is the first screen you will see. So make sure the IronTract challenge project is selected. And this hopefully works. It should be a quick overview of the platform. So make sure the project is selected again. Then you can open the scoreboard tab. And here you will see the ranking for both competitions. So for the HCP, but also for the overall competition. And you can also see the total number of submissions for each team. You can open the analysis tab, and so this is going to be the most important tab where all the actions will happen, like uploading and downloading the data, and we'll see more about that in a second. Right, so the next step is downloading the training data. So you want to go to the analysis tab, and here you want to hit get original data, and it is important that you here select pre-processed training data. You can download, select like some files, like for example, only the HCP data, or you can download all the files. And this will be downloaded as a zip file. After you download the training data, you can run your favorite tractography, reconstruction tractography method. We here ask participants from round 1 to use exactly the same orientation, reconstruction, and tractography methods that they use in round 1, whereas new participants just use your favorite method. Both previous and new participants, importantly, must use the harmonized pre-processing and seed region. Once you've done that, you can go on after you run your tractography methods. We ask you to post-process the data this time from 2. So after registering, you will receive a link to access 2 scripts. So the first script is compute density volume cpfl.py. This is going to do the post-processing 1. And so if you have TRK files, if the output of your tractography algorithm are TRK files, you can just use the script as it is. If you have tracked volumes, you need to apply the first step, which is the line thresholding on the fly in your tractography code, and then you can use the rest of the script on your output volumes. The second post-processing is compute density volumes vmc.py, and this also includes 2 inclusion masks, one for the training and one for the validation case. Again, if you have as output TRK files, you can just run the script as it is. If you have volumes, then you need to use the inclusion mask while you run your tractography algorithm, and then you can use the rest of the script on your output volumes. If you have any question on how to use the script, just please email us. These scripts will both produce different nifty volumes that you will have to put together as a zip file in order to upload to the QMENTA platform. We ask you to please submit results from this to post-processing separately. So how would you upload training data? Again, you go to the analysis tab, and here you want to hit upload training data. You select the acquisition scheme that you use, and please specify in the methods whether you whether these are data from postprocessing 1 or 2, and then you can just upload the zip file. Once you upload the zip file, this is going to show there, and then you need to show there, and you need to hit save. After you do that, everything's going to be, you don't need to do anything else. Data will be uploaded. It's going to tell you it's going to be uploaded successfully, and then it's going to start processing automatically, and you will receive an email when the process is done. So here you will see, you can see the 2 blue arrows there, which means that the analysis is still processing, and you can also see the processing bar. If you click on your analysis, you can see more about the state of your processing, and you can also check the data that you uploaded. Once the analysis is completed, you will see three dots, 3 green dots next to it, and also will say completed, and you will also see the AUC score next to it. You can then we have, for this round 2, we have a maximum of 10 uploads, but if you need more, please contact us. Then I was sure. Oh yeah, right. Sorry. So you can also check the results of when after you upload training data. So and you will do that by selecting your analysis, and then you can go on results and show results, and this will show you the RSC curve and the AUC score. You can also go back and you can also download the results, so you can do results again, and then you can do you can get the files. You can download the RSC figure and also report file. And here you can also visualize the volumes and check that they are in the right space by selecting it and visualize them. Right. So after this, and whenever you're ready, you can download the validation data. So you would have to do the same. You would have to go to your analysis tab and then get original data. And this time you want to download the pre-processed validation data. Again, you can either download some of the files or all of them, depending on which acquisition schemes you want to use. Always remember to download the injection mask. After downloading the data, again, you will have to run the post-processing as it did for the training data. Again, put everything together in a zip file before uploading to the QMENTA platform. But this time, we also ask you to include a PDF file that that describes the methods that you use, and this must include any information that you would need in order to replicate the results. Again, please submit both results separately for each of the 2 post-processing. So how you would upload the data, again, analysis and upload results. This time when upload validation, it's reminding you to upload the PDF file together. Just specify again which post-processing you use in the method section. And then you can just select the data. This time again, you will see the uploading successful uploaded data, but you won't see any score for the validation case. Right. So just to conclude, the deadline is again November 8th, and in order to finalize your submission, by then you need to upload the training data, the validation data, and the PDF method file. And for round 2, we're also asking you to share the code, and Gabriel is going to talk about it in a second. If you have any questions, please subscribe to the mailing list. You can find it on the IronTract Challenge website, or you can also email us. That's all I have to say.
Thank you. In the meantime, I don't know if anybody has any particular question right now. Remember you can write in the chats. And in the meantime, let me just share one slide. So got lost in my Sublime. You see, okay. All right. So to pick up on something that Anastasia was mentioning in the beginning, and picking up also in share your code. So one part that's very important that is being addressed in the challenge is about the methods themselves. But we all, as Anastasia was mentioning, like then what? Like how do you democratize the use of that code, or the reuse and these fantastic algorithms that everybody is creating? So like, how do we make these tools easy and accessible, so then they can be used by other researchers or even by clinicians in the end, right? That's the whole point, like how to accelerate this deployment of the algorithms, so then it can be used by clinical researchers or clinicians or other studies. So Gabriel will give us like a more in-depth tutorial with hardcore terminal kind of stuff. So I'll just show you some pretty pictures. I have the easy flashy part. No, but I just want to mention, like, the platform that you saw. So like behind the scenes, the vehicle that we use is Docker. It's simply Docker, where the developer, they pull, but then they put their code in. You can put your code in an image, then push it to the registry, and that's then associate or register, let's say, the tool in the platform, like in a simple interface. So just to, if there are any parameters, if there are, what's the entry points, like what's the script that will be initiated when the actual image is executed. And that connection is basically what allows that when the user, like what you saw before in the demo, like when the user has some data set already uploaded in the project, and then they say, I want to run this particular analysis. Behind the scenes, it will fetch, the platform will fetch the respective image, the respective version, get as well the associated, so the files, the nifties or the DICOMs or whatever files are from the patient record. So it will get them and download them inside this Docker image, execute the code or the binaries, and then push back the results to the platform. So this is like a very simple kind of 1, 2, 3 kind of steps to port, to share your code. Gabriel will show us like how that can be done. I think it's very simple, like in a couple of 1 to 2 hours or so, like it's up and running. And yeah, so I think it'll be the best to show us how that works. So I'll switch from the screen. Oh, I can stop sharing.
Thank you.
Okay.
Thank you, Paolo. All right, should see my screen now. All right, so yeah, Paolo and Anastasia invited me to try this code sharing approach with Docker. So I went over it this week, and it was quite, as Paolo said, it was quite easy to do in the end. And hopefully it will be even easier for you, since you can use everything that we'll be showing today to start, essentially. So the first thing to do is to get Docker installed on your machine. It's pretty straightforward. You can follow the instruction online and get Docker set up for your machine. And then you can up to this link on GitHub, where essentially all the code for the example I'm showing today is there. You can also look at the original example that QMENTA is giving online. There's some additional stuff there, but for the challenge, I guess this is a good start. So if you check out this GitHub, you will get a bunch of files. The most important one maybe is the Docker file, where you essentially set up the Docker image with which library and software that you need. So this was actually in the example, we start from the image that QMENTA has provided, and then you add whatever you need for your code. So here you have a matrix, for instance, and a bunch of library. In the end, I also add DIPy. So it's very simple to do, but essentially here you set the image the way with the library that you need. Then you will see two files, setting.json and setting value.json. Those things describe essentially what goes in as input to your Docker container. You should not need to modify them so much from this, but essentially here's the kind of the structure of the folder for the input files. It should be very similar to mine, depending on the way you upload the file on the platform. So this is not, I mean, this you can, there's a bunch of documentation on this online. You can follow the tutorial. Essentially all of this is described online. And the final file that I want to draw your attention to is this tool.py. So everything, all the magic happened here. So essentially, this is a Python script. Essentially, the first thing you do in the image is to gather the input. So here I'm showing mostly the files. So the diffusion file, the gradient file, also the ROI for the post-processing. So you get the file path within the Docker image. And then what I'm showing is an example from the DIPy tutorials. You can find all the documentation online in more details, but very simply, the first thing to do once you get the path to the file is to load the diffusion images and build the gradient table from there. One thing that is also very useful is to get the brain mass. You can do that with the media_node_su function of DIPy. And once you get that, you can start the modeling, the local modeling. Here I'm modeling with the diffusion tensor. So I'm setting the tensor model with the gradient table and then call the fit function. So I'm getting the diffusion tensor in all the voxels of the brain, and I can get my FA map. I do the same essentially with CSD, getting the response function from this function of DIPy, getting the constraints very called the convolution model with the gradient table and response, and fitting the CSD. So at this point, I have a tensor model, I have an FA map, I have a fit CSD model, so I can run Tractography. So in this case, we want to see the start Tractography in the injection site. So I'm loading the mask, setting a bunch of seeds. Here I'm setting 125 seed per voxel, and then I'm setting a probabilistic direction getter, so essentially a probabilistic Tractography that takes as input the CSD, which then I can set within my local tracking function. And at this point, when I'm running this line, I'm getting all the streamline from my CSD model. So essentially this is the piece of code you need to change with your local model, with your favorite Tractography algorithm. And then what I've put in this tool.py is the two scripts that Chiara showed before, compute density of TFL and compute density VUMC. So you can do it within the script. So as Chiara mentioned, essentially it's just a density map from visitation count of the streamlines, and you threshold this map on 200 time points, so you get a very broad density map that become more and more conservative, and from which you can build the ROC curve for the analysis, for the scoring. Similarly, for the VUMC, it's the very same code, but you will do an additional filtering of streamline reaching some ROI defined from Atlas. So at this point, you reach the final step of the script, which is essentially getting the data out of the Docker container and being accessible elsewhere. So this is the key file to modify, to share your code. When you're developing it and you want to test it locally, you need first to build Docker. This is usually done pretty fast. I just open the Docker image and add the different libraries. And when you're done with installing the different packages, it should be done very fast, you can now essentially test your code. There's a function test tool.py that essentially take your Docker image. So this is essentially my username. This is the name of my Docker image and a tag, essentially a version of the container. I give the input data, output data folder, and the parameters, and I can run the script locally, but within the Docker image. When everything is as I want, I can push my Docker online, and then it will be accessible through the QMENTA platform. So far, so good. I don't see the chat, but if there's questions.
Yeah, there's a question from Jesh. If your tool.py parsing is your tool.py parsing the JSON files?
This is done within the Docker image. You essentially have this the subject here, settings, and the context subject, from which you can query the input files and input files path and different parameters that you will set for your pipeline. I went very simple for this example. Most of the parameters are coded in the Python script, but you could have input parameter for each of the parameters that you would like to modify.
This context object is basically It's basically like what makes the link or the interface between the platforms. So like if a user clicks on a particular subject, like all the files or the description of the files and metadata and a couple of other things can be retrieved here. Also parameters that user defined, so they can be retrieved through this context object. So then inside the code, like it's dissociated from the user interface already. So then you can query the files or query by sequences and a bunch of other things.
Okay, so after the Docker push, essentially what I did is to put my Docker container online on app.docker.com. So I have my user ID, name of the container, and also the tag, which is version 1.1 here. So then I can up to QMENTA, and I need to, in this case, we need to go to the default project, which everyone should have when they sign up to QMENTA. So then you can up to analysis, and you want to go in my tools. When you go there, you can create a new tool, and essentially this window will pop, and you need to fill it. Again, there's a bunch of documentation online. You can follow the tutorial to do that. That's very straightforward to do. Essentially giving the name of the image and the links. You might need to set the interface here for some of the parameters for the inputs. And you might also give some description of the tool, of your tools. You hit the save tool, and now the tool is available for you to use for the processing. But first, before being able to use, you need some data, so you can up back to the IronTract challenge. And if you go in my analysis, you can, as Chiara showed, you can get the pre-processed data and the training data. You need to be careful here that the way you upload the file are also the way you read it in your tool, but this is just minor. So you can essentially download the data here, and then you go back to your project, default project. And at this point, you go on the data, and you can upload session data, which will be essentially just drag and dropping the data from the challenge, setting an ID, and you're ready to go. So this is already done with the training and validation data. So if I go in analysis, I can start a new analysis. Here I have my tool, tracking a track-based example, and then I can set a name, like demo, and I choose the data. I have two options, the training and the validation. Let's just choose the validation this time. Choose selected. And for the post-processing here, I made the option, you can either choose both or a PFL or the UMC. So let's do both, and then I'll start the analysis. And this should run on the platform, and so you will see the progress of the tool running on the platform. You can either go and look how the processing went. Actually, you can look at the different steps of the analysis, so running, DTI fitting, FOD fitting, tractography, and density map estimation. And finally, you go to the result, and you will have your, essentially, this is the file you need to download and upload to the challenge, as Chiara showed us before. Of course, you will need to include the description of your tools in the validation case, but otherwise, this file is the volume. So this zip file containing the 200 volume ready to be scored on the challenge. So essentially, you will download that, go back to the project, IronTract, and then you can go in the analysis and upload your result. We have already done that for the training one, PFL and DMC, and you get the score for those results. So this is the way I've been at least doing putting the code on the platform. It's running very smoothly, and that's it essentially. So, do you have questions?
All right, thank you. Any questions? Not let me share my screen. Okay. Whoop. So as I said in the chat, we'll be sharing like the slides and video later on, so we have like reference to all this documentation. But I just wanted to add one thing, or to clarify that you could see in your demo, but just to make sure that obviously the code it's there's different licenses, probably open source. So like you can also add like in one section of the when you're adding the tool to describe, like add the links to your repository, what are also like there's a section about kind of related to the methods or potential methods section, any publications reference. So like all this information will be visible to all the users. So it's speaking again on the words of democratizing the code sharing or the distribution as well of tools and image processing methods. That's the way that now we have been evolving to make sure that then like when somebody uses the code, it's also very easy to see what publications are needed, if there's any description of the methods, like to make things faster and easier for say the more applied groups perhaps, or some clinical research that wants to run population studies. So all of that is here, all these links, and we'll see the GitHub for the particular example for IronTract, so like it will make things easier for everybody. And if there's also any doubts, the team is here for you, to help you. So I would invite everybody to join us Slack space. So it's the Brain Innovation Hub. So we'll share this link. If you go to QMENTA.com and then the Brain Innovation Hub, it's an invitation link that everybody can use to join this Slack space, and then you have like support and any questions about the challenge itself, about the SDK technicalities. We are there. So I would invite everybody to go to this space, as some things will evolve as well, and some new novelties will be added to this initiative, let's call it, to follow on. Yeah, and then after all of this, the winners, the brave winners that passed through this round 1, round 2, that didn't procrastinate and accepted this second challenge. Like there's also, they share their code, or their best code. So we managed to also get some extra funds. So we'll be having 3 awards for the 3 winners. So there'll be the third one will have a $500 prize, cash prize, the second $1,000, and the first one $2,000. So that's, I'm very happy and very proud that we are starting, and probably the first of more challenges. And the only, to motivate as well, to make it more interesting, like the only inclusion criteria is to share your code in this way with Docker. So that will be kind of the inclusion criteria as a way to also motivate to democratize. Maybe it's a bit of like do this to democratize. But I would invite everybody to join this challenge. So as was mentioned, you have until the 8th of November. There will be also, besides the awards, there will be some follow-ups. We'll schedule another webinar, like to announce the winners. We also intend to, let's say, enlarge the scope of not only the participants of the challenge, but to also invite clinicians, clinical researchers, people, anybody that might be interested in the methods really go forwards and push for the next stage of let's distribute these great methods and these great algorithms. And to pick up on a question also that was mentioned earlier about the publications. So Anastasia was replying in the chat, but just for everybody, was somebody, I need to bring up the chat, was asking about if we're going to be discussing about the papers. So Anastasia can join in, but there's we'll be submitting another abstract for ISMRM, right, Fiona?
Yeah. So, thanks so much, Paolo, and thanks, Gabriel and Chiara, for all the work putting together this demo. So we are planning to submit another ISMRM abstract. The deadline this year is mid-December, and that's why we've set the deadline for the challenge to November 8th, so that there's enough time for Chiara to put together the results and prepare another submission. And then after that, we're on to the journal submission. And actually, I had one question. So, well, first of all, I want to say that it's you know, the best test was that Gabriel was able to just jump in and within a couple of days figure out how to share his code and how to do the stuff that he just showed. So are there any pro tips for any of our participants that might be coding in a compiled versus interpreted language? Would that, is that just something that they should come to the Slack or talk to you guys to get help with?
Both. So like you can just go to the Slack and then and make the particular question, but usually the way we do, because we use this internally as well for like building pipelines and workflows, is like if you have any, so the Python is just the entry point. So then in that Python code, you can just call whatever is your binary or MATLAB, compile MATLAB. There's if you can put something in a Docker, then it will work. The Python little script is just the interface, like a simple interface to connect the platform, the backend, and the user interface to the execution, the running of the actual, let's say, binaries or code. So there's absolutely no problem. But if there's any doubts, there's the documentation, and maybe the best is just join the Slack, and yeah, and we are there live to help you out.
Excellent, thank you.
There's a question on the chat. Do we have to get the entire Docker piece?
To be considered for the prize, you have to do it.
Yeah. So world fame or
fame or wealth, yeah, or both.
Fame or wealth, yeah. And there was another question before that you answered on the chat, like if maybe it's just if people didn't see the chat.
For the first round participants, right? So
yeah.
If you have already submitted for the first round, what we would like you to do is use exactly the same ODF recon and tractography method that you used then, but now use it with a new pre-processing and post-processing that we established to be best based on round one. So just remove the pre and post-processing steps for whatever you did. Use the pre-processed data as Chiara showed you. Do your recon and tractography, and then apply the two post-processing tools that that we distribute. So if by any chance you didn't get those, just email me and I'll point you to the Google folder where all those scripts are.
I'm just sharing the link to make it easier. Yeah. Yeah.
I should say that we would like to share the code from all the participants. So just in the interest of reproducibility and of open science, we would like to be able to share all the methods that enter the challenge. So, you know, don't just do it for the cash. For science too.
So the tandem that makes that is interesting, more well.
Exactly.
No, but so as a follow-up as well, like by sharing the code and not only the scripts, but sharing the code also as a Docker, then as a follow-up, then it also opens the possibilities to anybody to create workflows building or continuing from that Docker, from your method. So the same way that we are doing now from the pre and post processing, and now you're doing something new in Tractography. Let's say that all these methods will be available for the community, so then they don't have to go to GitHub and try to find and get the code, try to make it work. Then we will be doing some new ideas and a follow-up, so then you can just continue from that Docker or that set of Dockers.
Yeah, ultimately getting this to work for QMENTA users is the best test for how easy your method is to use in general.
Mm-hmm. Any further questions? Chat. Mm-hmm. If not, don't procrastinate for science. No, and again, a pleasure to have you all here, and for the putting this. Thanks everyone, and for putting this presentation and demos together to explain everything. I think it was pretty clear and simple. And again, as I wrote, like we'll be sharing the video and the slides, so then all the materials are accessible. And any questions, any doubts, we are here to help. So just shoot us an email or join the Slack, and we are there.
And a big thank you to QMENTA for hosting both the challenge and
yes, thank
you, and thank you guys for creating value. We are just here to help out. All right.
Hey.
So thanks everybody. Pleasure to see you online, at least, not in a conference somewhere, at some point. And have a great day or a great weekend, and see you around.
you, everybody.
Thank you.